Cantor's theorem. If A is any set, then there is no surjection of A onto the set Pi of all subsets of A. Proof. This theorem says that if A is any set and Pi is its power set, then it is not possible to define an onto map from A to P of A. Now let us illustrate this theorem by taking an example. Suppose A consisting of elements like x, y, z, then PA consists of all subsets of A, including A because A is a subset of A, and other subsets are like set x, set y, set z, set x, y, set y, set x, z, like that. Now suppose there exists a surjection F from A to PA, and it takes x to suppose set x, and it takes y to set y, and it takes z to set z. Then it is very clear from this that there are some more subsets like set x, y, set y, set x, z, etc., which are not the image of any elements of A. And also you remember that if A is having 3 elements or n elements, then the PA consists of 2 raised to n elements. So from this example, it clearly tells it is not possible to define a surjection from A to P of A. Now we are going to define this analytically by giving a good proof in using set theory idea. Suppose there exists a surjection map F from A to PA. See here, A, PA consists of all subsets like A is there, other subsets like this, and F is a surjection suppose from A to P of A. Now you take any subset B of A, that means an element of PA. Now since F is a surjection from A to PA, therefore there exists a B in A such that F maps B to B. That means for any B in PA, there exists an element B in B such that FB equal to B. Now B is in A and capital B is a subset of A like this. Now B may be in B sometimes and B may not be in B. This is the case. Now for any A in A, you take for any A in A, this F of A is a subset of A, an element of PA. There are two possibilities. This A may be in F of A sometimes, or A may not be in F of A. Now you consider the set D consisting of all the elements A in A for which A is not in F of A. Clearly D is a subset of A. Since F is a surjective map from A to PA, there exists an element A0 in A such that F of A0 is equal to D. So this is our D. D consists of elements of A such that A is not in F of A. Now this D is an element of PA. F is a surjection from A to PA, and therefore there exists an A0 in A such that F of A0 is equal to D. Now here there are two possibilities. A0 may be sometimes in D like this because D is a subset of A, and A0 may not be an element of D like this. Now let us take the case 1. Suppose A0 is in D. If A0 is in D, by the definition of elements of D, D consisting of those elements for which A is not in F of A. So if A0 is in D, A0 is not in F of A0. That is A0 is not in D because F of A0 is D. So A0 is not in D. So if you take A0 in D, you are getting A0 not in D. That's a contradiction. Now if you assume the second case, suppose A0 is not in D. So A0 is not an element of D, and therefore A0 is in F of A0 because D consists of those every element A in A for which A is not in F of A. Here A0 is not in D, therefore A0 is in F of A0. A naught is in f of a naught. That means a naught is in D. So you got a naught is not in D implies a naught is in D. So in any cases, if either a naught is in D, a naught is not in D, you are getting contradictions. Hence, what we assumed is wrong. It is not possible to define a surjection from A onto PA. That's all the proof. Thank you.